In this video, we're going to talk about substituted cyclohexanes. We're going to see how to switch between the different conformations and also how to decide which conformation is more stable. So when cyclohexanes have substituents, there are two possible non-equivalent chair conformations. Right? In the one, the substituent is in the axial position, and in the other, the substituent is in the equatorial position. And where I put this one substituent doesn't really matter. In each case, it's always going to have one where it's axial and one where it's equatorial. It's just a matter of how we're drawing it, which carbon atom it's on. One important thing that's going to be especially important when we have multiple substituents is to note that in the way that I've drawn this, if I've drawn it in such a way that it's up in one configuration, up in one conformation, it's going to be up in the other conformation as well, right? So when I go between the two chair conformations, everything switches. If it was axial, it becomes equatorial, but if it was up in the first one, it's still going to be up in the second one. Now, I mentioned on the last slide that the two chair conformations are not equivalent. And it turns out that the conformation where the substituent is in the equatorial position is much more stable than when it is in the axial position. And as a result of that, if I have this methyl cyclohexane, 95% of it is going to be in this chair conformation, and only 5% is going to be have the methyl in the axial position. So the reason the equatorial position is preferred is because of steric interactions when you have a substituent in the axial position. And so this is related to things that we talked about in Chapter 4. And one of the things we talked about in Chapter 4 is that this gauche interaction is unstable, right? And so this molecule, a more stable conformation would be to have the CH3 down here, so you don't have the two methyl groups butting heads. If the methyl is in an axial position, essentially we get that same type of gauche interaction between the methyl group and then the carbons in the ring. And so if the methyl group were to be here in the equatorial position, that would be preferred, right? Or, I kind of like this picture, right? When it's in the axial, right, things are bumping into each other, and they can get out of their way better when they're in the equatorial position. And so this interaction, this particular steric interaction that makes the conformation with the substituent in the equatorial positions more favorable is called a 1,3 diaxial interaction. All right, and not all substituents are created equally. The bigger the substituent, the greater a penalty for being in the axial position will be. And so what this tells us is, right, what is the energy penalty of having that group in the axial position? And so the greater the energy, the more unfavorable those 1,3 diaxial interactions are going to be, and the less likely we're going to find conformations where that group is in the axial position. And as a result, right, the higher the energy, right, the greater percent chance that that molecule is going to be in the equatorial position. Or it's going to be in the conformation that has the substituent in the equatorial position. Okay, so if we look at this compound, they want us to draw the two different chair conformations and then decide which one is more stable. All right, so I'm going to cheat. I'm going to start with the two chair conformations, and if you need help with these, go back and watch the video on drawing the chair conformations. So where we put the NH2 doesn't really matter because it's just monosubstituted, right? We can just kind of flip it around and put it on any one of those carbon atoms. So I like to be consistent. If I just have one substituent, if I kind of do things the same way, then I'm less likely to make a mistake. And so what I do is, if I have the option, I always number my carbons 1, 2, 3, 4, 5, 6. And so when I have this type of chair conformation, the head is always my carbon number 1, and that's where I always put, if I just have one substituent, that's where I'd always put it. And so in this first one, I'm going to put it in the axial position. All right, in my other conformation, right, when I go from this chair to this chair, what's happening is, right, the head in this one becomes the foot in this one, and the foot in this one becomes the head in this one. So when I'm numbering, right, this is my carbon 1, and then clockwise 2, 3, 4, 5, 6. It can be really easy to get these mixed up and to tell which atom in this conformation goes with which atom in this conformation. But if you're consistent and you always make the head, when I've drawn it this way, as 1, right, then that's going to switch to be the foot in the other one. And so when I go from this conformation to this one, right, it's still got to be on carbon 1, but when I flip between the two conformations, if it was axial in this one, then it's going to be equatorial in this one. All right, so these are the two conformations, and we just have one substituent, and so it's going to prefer the conformation where it can be in the equatorial position. So that one is more stable. Okay, now we can get more interesting when we have multiple substituents on my cyclohexane. And this is where the ups and downs become important. If I just have one substituent, then it's just sort of arbitrary whether I drew it up or down. I can just flip it over and it would have been the other one. So what we're really interested in when we have multiple substituents is it doesn't really matter that it's up or down. That's sort of arbitrary. But the reason we like to specify this is because we need to know what the substituents are relative to one another. And so generally, when they draw in this format, if they use a wedge, they're telling us that it's up. If they're using a dash, they're telling us that it's down. So if I was going to draw the two conformations of this molecule, again, I always like to put my first substituent on 1, then my second substituent is going to be on 2, and they told us that the chlorine is up. So the chlorine is going to be in the axial position on this one because the equatorial would have been down, right? And then the methyl is down, so that I know, right, that the down substituent in this one is going to be axial, the up in this one is the equatorial. And if I draw the other conformation, right, the chlorine went from axial, now it's equatorial, but it's still up, right? And the methyl, it went from axial to equatorial as well, but it's still down in both configurations. All right, so let's look at another example. So I've got a disubstituted cyclohexane. I've got two methyl groups. The first one is up and the second one is down. Now I'm going to cheat. I've got my sort of skeletal structures. And so if I'm going to put these guys in, and again, I always start, right, I'm going to make that. Sorry, I'm going to make this one 1, this one 2, 3, etc., right? And I'm going to put the first methyl on 1 and the second methyl on 2. And so the first one I'm going to make up. So the methyl has to be up. And then on the second one, it's dashed, so it's got to be down. And so, because that carbon is down, that is going to be the axial as well, right? And then when I switch to the other conformation, right, the atom that was the head is now the foot. So this is 1, this is 2, all right? And the methyl was axial here and up, so it's going to be equatorial and up in the other conformation. And then on carbon 2, it was axial and down, so now it's got to be equatorial and down. All right, and then they want to know which one is more stable. Well, in the one on the left, both methyls are axial. It doesn't like that. In this one, they're both equatorial, so the conformation where both methyl groups are equatorial is going to be preferred. Okay, one more example. Now I have a tri-substituted cyclohexane, but it works the same way. Again, I'm going to cheat. Right now, the first 3 carbons have substituents. So I've got 1, 2, and 3. Right, and then the foot is 1 on this one, so I've got 1, 2, and 3. And so my methyl group, I'm going to put on carbon 1, is down. Right, so the up is axial, the down is equatorial. So I've got my methyl group. On carbon 2, the chlorine is down. So on this one, the down is going to be axial. And then on carbon 3, the chlorine is up. All right, now I go to the other conformation. So now on carbon 1, the methyl, it went from equatorial, now it's going to be axial. It's still going to be down. On carbon 2, the chlorine is axial. Now it's going to become equatorial, but still down. All right, and then on carbon 3, it was axial. Now it's going to be equatorial, but still up. All right, so I've got my 2 conformations, and now I've got to decide which one is more stable. Now this is a little bit more tricky, right? Because in this one, I've got 2 chlorines that are axial and a methyl that's equatorial. So I've got 2 groups axial, that's bad, and 1 group equatorial, right? In this one, I've got 2 equatorials and 1 axial. So we might be tempted to say that this is the more stable, but we have to remember that not all substituents are created equal. And so if I go back to that table that we saw before, right? So a methyl that has a 1,3 diaxial interaction, right, that has an energy penalty of 7.6 kilojoules per mole, right? And a chlorine is only 2. And so 2 chlorines is still just 2 times 2 is 4. So even with 2 chlorines, that has an energy penalty of 4. That's still less than the 1 methyl at 7.6. So, right, when I have 2 chlorines that are axial, right, that gives me 4 kilojoules per mole of this diaxial interaction, right? But just 1 methyl in the axial position gives me 7.6, so that makes this the more stable conformation.